This is the most fun section in this unit, polar graphs, because they're fun to draw. Even with my poor drawing skills, they're fun to draw. So we're going to sketch graphs of polar equations by hand and with a graphing utility to check them, but you know that you're not going to have that graphing utility on test day. And then we'll write the equation from a polar graph. We're going to concentrate on three types: limacons, and there are three kinds of limacons. They're cardioids, which look kind of like a heart. There are dimpled limacons, and there are loopy limacons. Yes, those are math terms, dimpled and loopy. And there are roses and lemniscates. Roses always looks more like daisies to me, but that's okay. We'll call them roses. So here are cardioids. They can be oriented any way on the axes. So we start with the polar coordinates, and if you have, and the graphic I have has it as A plus B, but when they're cardioids, A and B are the same. So it's really A plus A cosine theta lives to the right of the x-axis of the pole. A minus A cosine theta lives mostly to the left of the pole. A plus A sine theta lives above the pole. And A minus A sine theta lives mostly below the pole. Now, as far as graphing those things, you don't really need to remember all that. I graph them by looking at what I call the big four, but we'll look at an example of that in a moment. Dimpled limacons have the exact same format, A plus or minus B cosine theta or A plus or minus B sine theta. And they have the same orientations. If you have cosine with a plus, then most of your graph is to the right of the pole. If you have cosine with a minus, most of your graph is to the left of the pole. If you have sine with a plus, most of your graph is above. Sine with a minus, most of your graph is below. And then loopy limacons have a little loop-de-doo in the middle. Same formats, it's just different relationships between A and B. If your plain old number is smaller than your coefficient, you get a loop. If your coefficient is smaller than your number, then you get a dimple. Here is how I sketch a limacon. I make a table for the big four. And the big four are 0, pi over 2, pi, and 3 pi over 2. Then I plot them on a graph. That kind of lets me know what kind of limacon I have. Well, if A and B are the same, you know it's a cardioid. So let's practice just using the big four method of graphing. First, I'll make my table. I make a column for theta, and theta is going to be 0, pi over 2, pi, 3 pi over 2. R is going to be equal to 2 plus 2 cosine theta. So 2 plus 2 times the cosine of 0 would be 4. 2 plus 2 times the cosine of pi over 2 is 2 plus 0. 2 plus 2 times the cosine of pi is 2 times negative 1, so 2 plus minus 2 is 0. And then 2 plus cosine of 3 pi over 2 is 0, so 2. So I'm going to grab a sheet of polar graph paper, which I printed out earlier. And I'll plot these points. 0, 1, 2, 3, 4. Pi over 2, 1, 2. Pi and 0. That's just the pole. And 3 pi over 2, I move down 2. And then I connect the dots with a smooth curve. That's it. There's the pretty solution. There's the really nice graph. My limacons are never round and puffy enough. They always look kind of flat. Okay, let's do a dimpled limacon. And we'll notice things about our table. You notice when we had a cardioid, we ended up with a 0 in our table. Example 2. I have theta. And I have 4 minus 3 sine theta. Now, if you remembered what I said about the A's and the B's, if the A is bigger than the B, you're going to get a dimple. But we'll figure that out from the table. 0, pi over 2, pi, 3 pi over 2. I plug in 0. I get 4 minus sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is minus 1, so 4 minus 3 is 7. So I'll plot those points. Zero, 4. 1, 2, 3, 4. Pi halves 1, so I only move up 1. At pi, I move 4 units, and 3 pi halves, I move down 7 units. Oops, that's 8, only 7. So I ended up with all positive numbers. All positive numbers in my chart means a dimpled limacon. So here's my little dimple. Whee! Looks something like that, except even more like that. Your limacons can be as much like a guitar pick as mine are. They don't have to be perfect. Now, how are we going to know when we have a loopy limacon? We will know from our table. Example 3. We have r equals 2 plus 5 cosine theta. So theta, 0, pi halves, pi, 3 pi halves, 2 plus 5 cosine theta. So 2 plus 5 times 1 is 5. Cosine of pi halves is 0, so just 2. Cosine of pi is negative 1, so I have 2 minus 5, negative 3. There's the loop. When you get that negative number, you got a loop. And then 2 plus 0 is 2. Oh, I'm running out of graph paper. I have to print some more. So, example 3. 0, 7. Pi over 2 and 2. Pi and negative 3. Oh, that means I go in the negative direction. There's the loop. And then 3 pi over 2 and 2. So think about the fact that you draw these things in a circle. So we start here, and our graph goes up here, and it's going to go through the pole, and then it's going to go around and hit that dot, and then it comes back around and ends up back where it started. So go on Desmos and play with these things and watch them graph. I'll take a minute and get Desmos up and we'll watch this one. So I went ahead and graphed it in Desmos, but I wanted to look at it piece by piece. So I duplicated the graph a few times and then I adjusted the range of theta. So if I take the whole graph away, if I look at just the piece from 0 to pi over 2, it makes this little top of the loop where my thetas are going from 0 to pi over 2. Next, it makes this little curly Q. As soon as it gets to pi, you can see that my R's are becoming negative. And actually, they become negative before I get to pi. They become negative as soon as 2r plus 5 cosine theta is less than 0. So here it goes through the pole and loops back. It stays negative until it gets back to the pole, and then it makes this little loop. And then finally, as theta goes from 3 pi halves to 2 pi, it makes the bottom piece of the loop. So they're drawn in a circle like that. So I always think about that's how polar graphs work. Okay, there's the step-by-step solution. So here, sketch the following polar graphs. Take a minute, see how you do. Check them on Desmos. Just by looking at it, I knew the first one was a cardioid because I have 5 and 5. But I went ahead and made my table. My table confirmed that I have a cardioid because I get a 0. That's where the little point of the cardioid is. So I plotted the points. I played connect the dots. It's not the best picture, but it shows the orientation. I have a sign. Most of the graph is below the x-axis. It's symmetric on the y-axis. So sine symmetric on the y-axis, cosine symmetric along the x-axis. Most of this lives to the left of the y-axis on the negative x-axis. So we had 4 minus 3. The A is bigger than the B. That means dimple. All these numbers are positive. Dimple. So I plotted, I played connect the dots. The last one is a sine with a plus sign, so I know that it lives mostly on the positive y-axis, and it's symmetric about the y-axis. My A is smaller than my B, so I expect loopy, and I got a minus sign, so indeed, it was loopy. So that is limacons. Let's talk about roses. Like I said, they look kind of like daisies to me. So the formulas that generate a rose curve always look like R equals a number times sine or cosine times your theta gets a coefficient. Depending upon whether the coefficient is even or odd, tells you how many petals you have. So roses. I'm going to write it down. R equals, and let's see, A cosine in theta, or R equals A sine in theta. A is the length of a petal. If n is even, then you have 2 n petals. If n is odd, then you have n petals. Not petals, but petals. I can spell. If you have a cosine, then the first petal lives on the x-axis. If you have sine, then your first petal lives in the first quadrant. Now, unfortunately, graphing them isn't as easy as the big 4. It depends upon the number of petals you have. So, I'm just going to jump into an example to show you how I do it. We're going to sketch r equals 2 cosine 4 theta. Equals 2 cosine 4 theta. Now we know a lot already. We know that the petal length is 2. And we know that since 4 is an even number, that there are 4 times 2 equals 8 petals. Since it has a cosine in it, I know that the first petal is on the x-axis. Now, since I know there are 8 petals and there's 2 pi radians around the circle, that means there is a petal every pi over 4 radians. So, really, without even plotting anything, we have a pretty darned good idea what it looks like. We could probably just draw it from this information. If you want to plot some points, you have to take the big 4, so 0, pi halves, pi, 3 pi halves, and divide everything by that number that's sitting next to theta. So I make a table with 0, pi over 8, pi over 4, and 3 pi over 8. So theta, 2 cosine 4 theta. 0, pi over 8, pi over 4, and 3 pi over 8. When I plug 0 in, I get 2. That's the first petal sitting there. At pi over 8, I plug in 2 times cosine of 4 times pi over 8, which is cosine of pi over 2. Which gives me 0. So I'm going to go ahead and get my graph paper up. Here's one. So I've made the first little part of a petal. Here's 2, and by the time theta gets to pi over 8, I'm back to 0. I made the little top half of a petal. At pi over 4, I plug in 2 cosine of 4 times pi over 4. So 2 times cosine of pi, which is 2 times minus 1, which is minus 2. So now I look at the point pi over 2 and I go to negative 2. So this brings me down to here. And then when I plug in pi over 8 cosine of 4, 3 pi over 8 is the same as 2 times cosine of 3 pi halves, which is 0. So I've made it back to 0. So you can do this again and again and again and draw all your petals. But we already know that our petals are spaced every pi over 4. So I have one here at this axis, and then I move pi over 4. There'll be another petal there. I move pi over 4. There'll be another petal there. I move pi over 4. There'll be another petal there. Another petal there. Oh, I ended up at the wrong spot there. This one should have been right here. So let me fix that. Yep, I didn't follow it correctly. It should have been right there. So make my petal here. There'll be one here, and then there'll be another one at pi over 4. So next it would come up here, here, and again, it's fun to go on Desmos and watch it draw your roses. Here's all the work I did. Whoop. And there's the pretty one. The petals don't really cross like they do when I draw them. I just do the best I can. So there, you can see I did another little loop around. I'd started with the first loop. See, there. We ended up with that first little loop and a half, and then I added another loop and a half. So we just graphed a rose with 2 cosine 4a. So anytime you have a rose, a cosine n theta, first thing you do is determine the number of petals. Number of petals, n if it's odd, 2n if n is even. The first petal lives on the x-axis. If n is odd, the petals will be at 2 pi over n intervals, because 2 pi is all the way around the unit circle. You have n petals, so there'll be one at every 2 pi over n. And if n is even, then it's 2 pi over 2n, or just pi over n intervals. Similarly, if we have a sine n theta, same thing for the number of petals, and I forgot to mention petal length is always a for either one of them. And the first petal, for if your function has sine in it, is going to be at pi over 2n. And we'll see why when we start looking at A here, this practice problem, because we're going to do this one together, and then I'll leave you to practice the 2 with odd number of petals on your own, and we'll compare answers. But part A, we have R is 4 sine 2 theta, and I went ahead and started it. The petal length is 4. That's the number right here. The number of petals is going to be 2 times 2, which is 4. Now, remember when we do our chart, we have to take the big 4 and divide by 2. Well, first I did our spacing. We have 2 pi over 4 petals, so pi over 2 is going to be the spacing. But let's look at the big 4. 0, pi halves, pi, 3 pi halves. And then I divide it by the number sitting next to theta. So 0, pi over 4, pi over 2, 3 pi over 4. So at 0, when you plug sine in, sine 4 times sine of 2 times 0 is equal to 0. So it starts at the pole. But then when I plug in pi over 4, I'll get r is equal to 4 times sine of 2 times pi over 4, which is 4 times sine of pi over 2, which is 4. So this pi over 2 divided by the coefficient is always going to be the location of your first petal. So 0, then the location of my first petal is at pi over 4, so 1, 2, 3, 4, because it's the length 4, and this is pi over 4, living between pi over 3 and pi over 6. So I know it starts here, it loops, it's going to go back to that center, because when I plug in pi over 2, I'll do it right down here. If I plug in pi over 2, I'll go ahead and make my whole chart. Theta and 4 sine 2 theta. 0, pi over 4, pi over 2, 3 pi over 4. When we plugged 0 in, we got 0. When we plugged pi over 4 in, we got 4 times 2 sine, which is 4 times sine of pi halves, which is 4. And then I have 4 times the sine of 2 times pi over 2. That gives me 0, so I'm back here. And then at 3 pi over 4, sine of 2 times 3 pi over 4 is 4 times the sine of 3 pi halves, and sine of 3 pi halves is -1, so this is -4. So instead of being over here at 3 pi over 4, I move 1, 2, 3, 4 in the negative direction. And again, we had already figured out that the spacing was pi over 2. So pi over 2 away from pi over 4 would be 3 pi over 4. Pi over 2 away from 3 pi over 4 is 5 pi over 4. And then we end up at 7 pi over 4. And yeah, I have to make that petal look a little better. And we look something like, should be at 4s, not 5s. I plotted 5s instead of 4s. And the pretty picture is something like that. They don't have to be perfect, they just have to have the right number of petals in the right locations. So try B and C on your own. We'll come back, we'll compare answers. Okay, so figured out my petal length is 2. I figured out that there are 5 petals because the number sitting next to theta is odd, so that's the number of petals. So the spacing is at 2 pi over 5. I got the common denominator of 10 because my first petal is going to be at pi over 2 divided by 5. Because remember, if we looked at the big 4, we would take pi over 2 divided by 5, which is pi over 10. So I found my first petal. I added the spacing, I added the spacing, I added the spacing. I plotted the ends of the petal, and then I drew in the rows. Try the next one. Petal length 3, 3 petals. Looks pretty easy. Okay, like we said, 3 petals, length 3. It has cosine in it, so the first petal lives here on the x-axis. And then their spacing is 2 pi divided by the number of petals, because it's 3. So 2 pi over 3. So my next petal is at 2 pi over 3. I add 2 pi over 3. So I just plotted the ends of the petals, and then I drew in the loops and made it pretty. Next and final polar graph we're going to talk about are lemniscates. They look like infinities. And they are the ones that have r squared in them. So we have basic ideas of what our different things look like. I'm going to find my first page. So on the first page, I told you we were going to do 3 different things. You can recognize limesons. They always look like r equals a plus or minus b trig function, cosine theta, or r equals a plus or minus b sine theta. Then we have roses. They always look like r equals a cosine n theta or a sine n theta. And finally, we have lemniscates that always look like r squared equals plus or minus a squared cosine of 2 theta, or r squared equals plus or minus a squared sine of 2 theta. So, easy enough. They're symmetric about the pole, and they're symmetric about either the x-axis, the y-axis, the identity line, or the negative identity line. So when I'm graphing a lemniscate, let me go ahead and look at example 5. We have r squared is 4 cosine 2 theta. I like to look at where the ends of my infinity symbol are going to end up. So if it has cosine in it, I know that cosine is at its maximum at theta equals 0 or 2 pi. So I'm going to plug 0 in. So theta equals 0, then r squared is equal to 4. So r is equal to plus or minus square root of 4, which is 2. So 2, I know what it looks like. Infinity. There's the pretty answer. So let's practice some more lemniscates. We'll do one with sine, and then I'll let you do the negative ones, and we'll meet back and compare. So I have r squared equals 25 sine of 2 theta. So I know that sine is at its maximum at pi halves. So I'm going to plug in theta equals pi over 4. So r squared is equal to 25 times sine of 2 times pi over 4 is pi over 2, which is 1. So r squared equals 25. R equals plus or minus square root of 25, which is 5. So I come here and I do pi over 4 and 5, pi over 4 and negative 5, and I draw in my little bow tie, my little infinity symbol. Now, for b, we have r squared equals negative 16 cosine 2 theta. R squared's never negative, so I need cosine of 2 theta. When does cosine 2 theta equal negative 1? Then I can have negative times a negative gives me a positive. Well, cosine of 2 theta equals negative 1 when 2 theta equals, not negative, when 2 theta equals pi. So when theta equals pi over 2. So now you finish it and sketch your graph, and you should be able to figure out what to plug in for C also. So we'll come back and we'll compare both of those. Okay, so if theta is equal to pi over 2, r squared is negative times negative gives me positive 16. So I can take the square root. So at pi over 2, we have positive 4 and negative 4. Draw in the loop-de-doos. C, I needed sine to be negative 1. So sine of 2 theta equals negative 1 when 2 theta is 3 pi over 2, because sine is negative 1 at 3 pi halves. So I divided by 2. So at 3 pi over 4, I can plug into sine of 2 theta. Negative 1 comes out. So r is plus or minus 3. So next thing we're going to do is to figure out the equation from a graph. So I'm going to get some notebook paper for this. I went ahead and wrote down my step 1. Identify what kind of graph you have. I have a cardioid. So I'm going to call it part A, even though I didn't label them in parts. This is a cardioid. And spell it correctly. Cardioid. Okay. Then, now I know it's a cardioid. Does it have sine or cosine in it? Well, it lives with most of it on the y-axis. Which implies it's of the form r equals a plus a sine theta, plus or minus. Then I find out that it's below the x-axis. In other words, it's on the negative y-axis. So that means it's r equals a minus a sine theta. Then I need to know what a is. So I make this bigger so I can figure that out. Let's see. Now I can see it. It's crossing at 1, 2, 3. So where do the minor axes cross? Because that's what A is. Where does it cross the x-axis? And that's at 3, so it is r equals 3 minus 3 sine theta. Now, when you're doing these homework problems, I would encourage you to plug that into Desmos and see if it works. Let's look at B now. Let's see if I can get B on the screen. There we go. So, what type of graph do I have? I have a rose. Where's the first petal? The first petal is on the x-axis. That means we have the form r equals a cosine n theta. How many petals do I have? I have 4 petals. Four is even. So n is equal to 4 over 2. So I know r equals a cosine 2 theta. How long are the petals? They are 1, 2, 3 units long. So r equals 3 cosine 2 theta. One more. Okay, so now I have a limacon, and it's a loopy limacon. So what do I have? I have a loopy limacon. I look at where it's located. So it's living mostly on the negative x-axis. So I'm expecting r equals a minus b cosine theta. X-axis means cosine. Negative x-axis means minus cosine. Now, where does it cross the x-axis? The y-axis, excuse me. Where does it cross the y-axis? It lives on the x-axis. Where does it cross the y-axis? That's when cosine is equal to 0, and when cosine is equal to 0, that gives me my a. So it crosses the y-axis at plus or minus 3, so I know r is equal to 3 minus b cosine theta. I know at pi, cosine is equal to negative 1. So I know when theta is equal to pi, I have r equals a, which I already figured out was 3, because we crossed the y-axis at plus or minus 3, minus b times cosine of theta is negative 1. But at theta equals pi, I'm at 7. So 7 equals 3 plus b, which means b has to be equal to 4. So r equals 3 plus minus 4. So that's 8. Okay. Even I made it big and I still wrote down the wrong thing. This is 8. So B is 5 because 8 is 3 plus 5. So R is equal to 3 minus 5 cosine theta. And you can check because when theta equals 0, then R is equal to 3 minus 5 times 1, which is negative 2, which is this point right here. So I finally got it right once I wrote down the right numbers. Okay, I'm going to make this smaller and then we'll pull up the ones for you to practice. Okay, look these over, give them some practice. Identify the type of graph. You got a dimpled limousin, you got a lemniscate, and you got a 3-petaled rose. So you have a good idea of what your format's going to be. Try them all. We'll come back and we'll compare answers. So starting with the dimpled limousin, it lives mostly on that positive x-axis. So we know that it's a plus b cosine theta. It crosses the y-axis at plus or minus 4. So I know that it's r equals 4 plus b cosine theta. If theta is equal to 0, then cosine is equal to 1. So I look at where it crosses over here on the positive x-axis, and it's at 7. So 7 is equal to 4 plus b, because cosine is equal to 1. So b is equal to 3. And you can check it by looking at Desmos. Let's look at the next one. We have a lemniscate. And I look at where the lemniscate has the ends of its infinity symbol. And that happens at plus or minus pi over 4. Here's pi over 4, and then minus pi over 4 if you were graphing a polar coordinate. So at plus or minus pi over 4, so r squared is equal to a squared. Actually, it's no positive because it's positive, yeah. If it were at 3 pi over 4, then you would need a negative sign. But it's at pi over 4, so r squared equals a squared sine 2 theta. Its length is equal to 5, so that's a, and r squared is 25 sine 2 theta. Now, if you want to check this on Desmos, you can't put in r squared equals 25 sine 2a. You have to do r equals the square root of 25 sine of 2 theta. And then finally we had a 3-petaled rose, and I looked at the length of the petal, and I looked at where the first petal lives. It lives there at pi over 6. So since it doesn't live on the x-axis, I know that it has sine in it. And so 4, which is the petal length, times sine of 3 theta. So you got lots of practice in your lab manual and your WebAssign. You can do this. These curves are fun to play with. Go forth and practice.